All right, welcome. Today, we are pulling back the curtain on the invisible foundation of our entire digital world, database architecture. We're going to demystify how pretty much every single piece of information you touch is organized, stored, and, brought back to you when you need it.
I mean, just think about it for a second. Every single social media post you scroll past, every online purchase you make, all of that data has to live somewhere. So the really big question for our digital age is this: how on earth do we design systems that are strong enough, but also flexible enough to handle this unbelievable ocean of information?
So, to make this all a little more concrete, let's play a role. For the next few minutes, you're not just watching, you are a digital architect. Our building materials aren't steel and glass. No, they're logic and code. And together, we are going to design and build a skyscraper made to house information itself.
So, here's our construction plan for today. We're going to start with the absolute core blueprint. That's the data models and schemas. Then, we'll look at the three-layered master plan that kind of governs the whole structure. After that, we'll learn the languages we use to build and manage the thing, see how users actually get in and access the building, and then, finally, we'll zoom out and admire the entire city of data skyscrapers we've all built.
Okay, first things first. Every great building starts with a great plan. And in our world, that plan starts with data models and schemas. This is the absolute first step. It's the foundation that everything else gets built on.
So, what in the world is a data model? Well, you can think of it as the fundamental rulebook for our entire project. It's kind of like the laws of physics for our data skyscraper. It defines our basic building blocks, like whether a piece of data is text, or a number, or a date, and it also sets up the rules, the constraints, that make sure our final structure is actually sound and the information inside is reliable.
Now this is a really crucial distinction to get. On one side, you have the schema. That's the permanent, detailed blueprint. It defines the structure and the rules, what we call the intention, and it almost never changes. But on the other side, you've got the database state. Think of that as the living, breathing building at any given moment, filled with actual data. This is the extension, and it's changing all the time.
And here you can see that idea in action perfectly. On the left, that's the schema, just the abstract structure, defining tables for things like student and course. It's just the plan, right? Now look to the right. That's the state. The tables are now filled with actual student names and courses. This is our skyscraper, fully populated, the blueprint brought to life.
So, we have our blueprint. But, a real skyscraper has to serve all kinds of different people, from folks in the lobby to the bigwigs in the penthouse. And for that, you need a master plan for flexibility. Which brings us right to the three-layered architecture.
And this right here is that master plan in action. The three-schema architecture. It's a genius idea that separates the database into three distinct layers. So if you follow the diagram from the top, you've got the external level. That's what you, the end user, actually see. Customized views for whatever you need to do. In the middle, you've got the conceptual level. That's our complete master blueprint of the whole thing. And way down at the bottom is the internal level, which describes how the data is physically stored on the hard drives and all that.
Now, this separation gives us some incredible flexibility. The first huge benefit is something called logical data independence. What this really means is that we can change the master blueprint, that conceptual schema in the middle, without breaking what our users see on the outside. It's like adding a whole new wing to our skyscraper without anyone on the top floor even knowing that construction is happening. It lets developers change and improve the database without messing up existing apps. It's a huge deal.
And the second superpower we get is physical data independence. This lets us completely change how the data is physically stored, that's the internal schema at the bottom, without touching the master blueprint at all. We can reorganize files, move to way faster hardware to boost performance, and it's like upgrading the entire plumbing and electrical system of our skyscraper without anyone inside even noticing. It's absolutely crucial for keeping things running fast.
All right, so we've got our blueprint and we've got our master plan. But how do we actually, communicate our instructions? That brings us to our next section, the languages we use to actually build and manage our data skyscraper. We basically use two main languages here. First up is DDL, the data definition language. You should think of this as the architect's language. It's used to build the schema, to create the tables and define all the rules. Then there's DML, the data manipulation language. This is the language for the building manager. It's used to work with the data inside the structure. Putting data in, changing it, and getting it back out. And within DML, there's a really important difference in style. High-level or declarative languages like SQL were an absolute revolution. With SQL, you just state what you want.
For example, get me all the employees in the sales department. The system figures out the best way to do it. On the other hand, low-level or procedural languages force you to spell out how to get the data, step by agonizing step. This leap from telling the computer how to just telling it what changed everything and made data so much more accessible.
So, our skyscraper is built, it's full of data, and we know the languages to manage it. Now, how do people actually get inside and use it? Let's talk about accessing the data.
You know, back in the early days of computing, everything was centralized. The database software, the hardware, the apps, it all lived together on one gigantic mainframe computer. Users would connect with these really simple terminals, but all the real work, all the processing, happened in that one spot. It was truly a single self-contained building.
But yeah, that monolithic approach just couldn't keep up with the explosion of the internet. A single building has its limits, right? The modern world demanded a totally new architecture, one that was spread out, specialized, and could scale up way, way bigger.
And the solution was the client-server model, which was a massive leap in design. It smartly divides all the work into two tiers. The client, that's your computer, handles the user interface and just makes requests. The server is a powerful, specialized machine that's dedicated to providing a service, like managing the database or hosting a website. This shift was like going from a single, all-in-one building to an entire campus of specialized facilities.
Most modern web apps you use today actually use an even more robust model, the three-tier architecture. So Tier 1 is the client, that's your web browser. When you click on something, it talks to Tier 2, the application server. This is the brain of the whole operation. It handles all the business rules and logic. And crucially, only the application server is allowed to talk to Tier 3, the database server. This creates a super secure vault for our data, adding a really important layer of logic and protection.
Okay, so far we've been really focused on designing our one skyscraper. For our last section, let's zoom out. Let's look at the entire city, the vast and varied landscape of all the database systems out there. The architectural styles of our data city have evolved like crazy over the years. We started way back in the 60s with these complex network and rigid hierarchical models. But the real game changer came in 1970 with the relational model. Its idea of organizing data into simple, intuitive tables was so powerful and effective that it became the gold standard for decades. And today, that city is more diverse than ever, with relational systems living right alongside a new generation of NoSQL databases built for the wild demands of modern data.
And we can classify all the different buildings in our data city in a bunch of ways. We can sort them by their data model, by the number of users they can support from just 1 to millions. We can sort them by their location, whether they're all in one place or spread out, and even by cost, from incredibly powerful free open source systems all the way to massive commercial platforms that cost millions of dollars.
So we've gone on quite a journey, from a single blueprint to a massive, sprawling digital city. And the most important thing to take away from all this is that none of it is an accident. Every layer, every model is a deliberate design choice, all aimed at keeping our data organized, secure, and easy to get to. And that leaves us with one final, really important question. As data becomes the very foundation of our world, what new architectural blueprints are we going to have to invent for the skyscrapers of tomorrow?